Stellar evolution is a process that tells us how stars change throughout their lifetime. Why do we care, I hear you say? Because stellar evolution is responsible for the production of most of the elements found here on Earth, and hence responsible for your existence. Now you're listening. Stars evolve differently based on their mass at the time of their creation. As Professor Raman Prinja of UCL would stress, birth mass matters. Get that on a t-shirt. Stars of all masses begin as a nebula, which is a huge cloud of hydrogen gas and dust. Gravitational forces pull the gas and dust particles closer together, causing the huge cloud to slowly contract and increase in density. As contraction continues, a ball of dust and gas forms, called a protostar. The contraction causes the dust and gas to heat up, as gravitational potential energy is transferred to kinetic energy and then to thermal energy. As particles get closer together, they begin to collide, creating a thermal pressure, which counters the gravitational pressure. With a continuation of contraction, a core is formed and temperature further increases, leading us on to a pre-main sequence star, or in short, PMS star. The temperature is now high enough for the PMS star to glow. As matter continues to accrete onto the PMS star, temperatures are high enough to fuse hydrogen into helium, creating a main sequence star.
About 90% of all stars in the universe are main sequence stars because this is the longest period of a lifetime of a star. A main sequence star is any star that is fusing hydrogen in its core and has a stable balance between outward forces due to thermal pressure and inward gravitational forces. Stars fuse hydrogen to helium in their core following the proton-proton chain reaction. A Hertzsprung-Russell diagram plots all stars by their luminosity against their temperature. The diagonal running from the top left corner where the hot luminous giants are to the bottom right corner where the cooler less luminous stars are is the main sequence of stars. Over the main sequence of stars we can find the giants and supergiants, while below the main sequence we find the white dwarf stars.
Over time, the star will use up all of its hydrogen reserves in fusion, and when this happens, the thermal pressure will decrease to such an extent that the core collapses. This collapse produces such vast heat because of the increase in pressure that a new fusion process will ignite, that of helium to larger elements like carbon and oxygen. This produces enormous thermal forces, causing the star to expand so large that its edges will cool. This is the red giant stage. Some stars have so much mass that they can continue this fusion process, with carbon forming neon, sodium, and magnesium. Again, the star begins collapsing when carbon runs out until temperatures are high enough for neon burning. This is followed by oxygen burning and silicon burning, which forms iron, nickel, and zinc. At this stage, the star can no longer perform fusion. It is now a supergiant.
Average stars like our Sun of masses between 0.8 solar masses and 8 solar masses will become a planetary nebula after the red giant phase. Afterwards, these stars become white dwarfs, very dense stellar remnants of up to 1.44 solar masses. White dwarfs do not create any internal pressure, so the pull of gravity is strong enough to make electrons get very close to each other and produce electron degeneracy pressure. This pressure is a consequence of Pauli exclusion principle, which states that two electrons with the same spin cannot occupy the same energy level. In other words, two identical electrons can't be at the same position, so when they're squeezed together, they exert pressure outwards, opposing the gravitational force. White dwarfs have a peculiar property. The greater the mass is, the smaller they are. However, there is a mass limit of 1.44 solar masses for white dwarfs, known as the Chandrasekhar limit. Above this limit, there would be no balance between the electron degeneracy pressure and gravity. Stars which are greater than 8 solar masses venture into a more flamboyant end stage. After the supergiant phase, its core contracts and gets hotter, making the outer layers fall inward, transforming protons and electrons into neutrons and neutrinos. Once the core collapse is halted by the neutron degeneracy pressure, it bounces back and produces a shock wave that blows all the materials out in an explosion called supernova.
After the collapse of a star, if its mass is greater than the Chandrasekhar limit, it will continue collapsing as pressures exceed the electron degeneracy pressure. Most protons and electrons fuse by a process known as electron capture. A neutron star is born. At this point, if its mass is below 2.8 solar masses, it will approach the degeneracy limit of neutrons. This sends out a powerful shock wave, stripping the star of everything except neutrons and a small number of protons and electrons. The stellar core is, by this time, just a 20-kilometer diameter ball of neutrons, which is so dense that a teaspoon of it would have the same mass as 10 Burj Khalifas. Because of conservation of angular momentum laws, which apply throughout the course of the star's collapse, the neutron star is now rotating at phenomenal speeds. It also has an extremely strong magnetic field emanating from its poles. When its rotational axis and magnetic axis are not aligned, this produces a lighthouse effect and is responsible for the pulsars which we can observe from Earth.
If the core mass of the star at death is greater than 3 solar masses, the neutron star will collapse to a black hole, where there is a singularity. This means the volume of the black hole is 0 and density infinite. The black hole is contained within a radius called the Schwarzschild radius, aka the event horizon. Nothing, not even light, can escape from within the Schwarzschild radius, so the escape velocity is equal to the speed of light. The radius can be calculated using the following equation.